Aero Engineering Thermodynamics. This is expected since a rigid tank has a constant volume and dV equals 0 in this equation. Therefore, there is no boundary work done during this process. That is, the boundary work done during a constant volume process is always 0. This is also evident from the PV diagram of the process. The area under the process curve is 0. The piston cylinder device initially contains 0.4 meter 3 of air at 100 kPa and 80 degrees C. The air is now compressed to 0.1 meter 3 in such a way that the temperature inside the cylinder remains constant. Determine the work done during this process. Solution: air in a piston cylinder device is compressed isothermally. The boundary work done is to be determined. V1 equals 0.4 meter 3 P1 equals 100 kPa D1 equals 100 degrees C V2 equals 0.1 meter 3. For an ideal gas at constant temperature T0, the negative sign indicates that this work is done on the system work input, which is always the case for compression processes. MECHANICS of energy transfer, heat transfer Q, work transfer W, mass flow M. Mechanisms of energy transfer. Energy can be transferred to or from a system in three forms: heat, work and mass flow. Heat transfer Q. Heat transfer to a system. Heat gain increases the energy of the molecules and thus the internal energy of the system, and heat transfer from a system. Heat loss decreases it since the energy transferred out as heat comes from the energy of the molecules of the system. Work transfer W. An energy interaction that is not caused by a temperature difference between a system and its surroundings is work. The rising piston, the rotating shaft, and an electrical wire crossing the system's boundaries are all associated with work interactions. Work transfer to a system, i.e., work done on a system increases the energy of the system, and work transfer from a system, i.e., work done by the system decreases it since the energy transferred out as work comes from the energy contained in the system. Car engines and hydraulic, steam, or gas turbines produce work while compressors, pumps, and mixers consume work. Mass flow M. Mass flow in and out of the system serves as an additional mechanism of energy transfer. When mass enters a system, the energy of the system increases because mass carries energy with it. In fact, mass is energy. Likewise, when some mass leaves the system, the energy contained within the system decreases because the leaving mass takes out some energy with it. For example, when some hot water is taken out of a water heater and is replaced by the same amount of cold water, the energy content of the hot water tank, the control volume, decreases as a result of this mass interaction. Heat transfer: if the temperature increases, then internal energy also increases. If temperature decreases, then internal energy also decreases. Examples of work transfer: windmill compressor. First law of thermodynamics for open systems: the sum of change in heat, work and mass is equal to energy change in a system. For adiabatic process, Q is equal to 0. If there is no rotary device, work done is equal to 0. If the system is in steady state, then energy change in a system is 0. energy is the sum of enthalpy, kinetic energy and potential energy. Enthalpy is the sum of internal energy plus product of pressure and volume, where PV is called the flow work or flow energy. Energy balance change in total energy of the system is equal to total energy entering the system minus total energy leaving the system. Energy change is equal to energy at final state minus energy at initial state. If the system is stationary or there is no change in velocity and no elevation, the change in the total energy of a system during a process is the sum of the changes in its internal, kinetic, and potential energies and can be expressed as for stationary systems. The changes in kinetic and potential energies are zero and the total energy change in below relation reduces to change in total energy is equal to change in internal energy. For non-flowing fluid, the total energy is equal to internal energy plus kinetic energy plus potential energy, whereas for non-flowing fluid, total energy is equal to flow energy plus internal energy, which is enthalpy plus kinetic and potential energy. Energy balance for closed systems. For a closed system undergoing a cycle, the initial and final states are identical, and thus E system equals E2, E1 equals 0. Then the energy balance for a cycle simplifies to sign E out equals 0 or sign equals E out. Noting that a closed system does not involve any mass flow across its boundaries, the energy balance for a cycle can be expressed in terms of heat and work interactions as net work output is equal to net heat input. For a cycle delta E equals 0. Thus delta Q equals W. Various forms of the first law relation for closed systems. Some steady flow engineering devices. Many engineering devices operate essentially under the same conditions for long periods of time. The components of a steam power plant, turbines, compressors, heat exchangers, and pumps, for example, operate non-stop for months before the system is shut down for maintenance. Therefore, these devices can be conveniently analyzed as steady flow devices. Nozzles and diffusers. Nozzles and diffusers are commonly utilized in jet engines, rockets, spacecraft, and even garden hoses. The nozzle is a device that increases the velocity of a fluid at the expense of pressure. The diffuser is a device that increases the pressure of a fluid by slowing it down. Nozzles and diffusers, that is, nozzles and diffusers perform opposite tasks. The cross-sectional area of a nozzle decreases in the flow direction for subsonic flows and increases for supersonic flows. The reverse is true for diffusers. The rate of heat transfer between the fluid flowing through a nozzle or a diffuser and the surroundings is usually very small, Q equals 0, since the fluid has high velocities, and thus it does not spend enough time in the device for any significant heat transfer to take place. Nozzles and diffusers typically involve no work, W equals 0, and any change in potential energy is negligible, delta P equals 0. But nozzles and diffusers usually involve very high velocities, and as a fluid passes through a nozzle or diffuser, it experiences large changes in its velocity. Therefore, the kinetic energy changes must be accounted for in analyzing the flow through these devices. F the L to K is not equal to 0. Turbines and compressors in steam, gas, or hydroelectric power plants The device that drives the electric generator is the turbine. As the fluid passes through the turbine, work is done against the blades, which are attached to the shaft. As a result, the shaft rotates, and the turbine produces work. Compressors, as well as pumps and fans, are devices used to increase the pressure of a fluid. Work is supplied to these devices from an external source through a rotating shaft. Therefore, compressors involve work inputs. Even though these three devices function similarly, they do differ in the tasks they perform. A fan increases the pressure of a gas slightly and is mainly used to mobilize a gas. A compressor is capable of compressing the gas to very high pressures. Pumps work very much like compressors except that they handle liquids instead of gases. Note that turbines produce power output whereas compressors, pumps, and fans require power input. Heat transfer from turbines is usually negligible, Q equals 0, since they are typically well insulated. Heat transfer is also negligible for compressors unless there is intentional cooling. Potential energy changes are negligible for all of these devices. Delta P is equal to 0.